Okay, thank you. Thank you to the organizers, and thank you everyone who's here to chat about this topic. I think this is a very exciting time. Of course, the whole world knows that it's exciting for AI, but we here also know that it's an exciting time for quantum. And I think part of the point that I think has been echoed by a lot of the speakers in this session and also more broadly is that these topics they go hand in hand. It's not like an either-or thing. Quantum and AI are technologies that naturally work together, right? AI is an enabler of quantum, and of course, quantum is bringing capabilities that AI alone cannot handle. So let me say a word real quick about SandboxAQ and what our interest is and how we relate to these ideas. SandboxAQ as a company, we're a place that is interested in solving hard problems, in applications, in doing things that, not in, of course we're developing the technology, at the frontiers in order to solve these problems, but our main goal is to solve the problems. And whether the tools are AI tools or quantum tools or whatever tools, we don't care. And so for us, when we look at the topic of quantum technologies, for example, what we see is, yes, quantum computing gets most of the attention, even here at this conference, but is not yet ready to actually be used for practical problems. Maybe one day when we have scaled fault-tolerant computers, or perhaps sooner if we get lucky, that will happen. But we can prepare today to use the quantum computing power of tomorrow by building out the rest of the systems that will be required. And then there are other aspects of quantum technologies as well that get less attention, things like quantum sensing, for instance, which actually can be used today to solve real problems. And I'll mention a couple of the examples that we work on in a few minutes. And then, given this sort of view of the quantum technology space, what about the AI side? Well, AI, I think, has already been discussed as an enabler of quantum technologies, as a key ingredient to solve kinds of problems. But what do we mean by AI? AI means a lot of stuff, and a lot of the attention these days is on large language models and things like that, ChatGPT, et cetera. But that's not necessarily the kind of AI that we're interested in right now. It's not these sort of language-based models. They're great for solving language-based problems or maybe image-based problems, things like that. But the kind of AI that's more along the lines of working with quantum technologies to solve problems in quantitative arenas is more of a quantitative AI, right? It's an AI that has to do with numbers, and that's really the foundational technology that enables the rest of what's going on. And so when we at Sandbox talk about AI, we like to talk about not large language models, but the idea of the next generation of quantitative AI, which we might call a large quantitative model. And so this is the kind of way that we would like to be thinking about it. So in these areas where physics and chemistry and biology and all of these kinds of places where we expect quantum computing to one day make a serious impact, along with that will come new quantitative kinds of AI. And the domains in which these quantitative approaches, different kinds of computing will make impact is actually much greater than just where we might see purely language-based impact. In fact, I think something that's happening in the world right now, organizations that are trying out large language models for all these kinds of problems are realizing that, oh, actually, if I'm interested in developing a novel drug or a novel material or figuring out how things work at the molecular level, well, a large language model is not going to do it. You need a different kind of computing, different kind of AI, and eventually quantum computing in order to handle that sort of thing. And this goes for sensing as well. So the major problem in the sensing arena is not even so much, on one level you've got the hardware which can detect tiny changes in the environment, and quantum sensors are revolutionary for that kind of thing. But how do you interpret the signal? There's the problem is almost that they're too sensitive, right? It's the sensing version of the problem in quantum computing of calibration and error correction and stuff like that. And that is the kind of thing that is not going to be solved with a language model alone. So let's talk about a couple of examples. So a few things that we work on at SandboxAQ, just to highlight some of this stuff. So the first one that I'll mention is a sensing example that in our division that we call AQNav. So this is navigation with magnetic anomalies. The idea is to combine sensing, quantum sensing, with AI in order to solve a problem which is a very real problem, and it's a very real problem today, and we can deploy a solution today. So what is that problem? The problem is, GPS denial, GPS blocking. So a lot of times one thinks of this as a problem, as like a defense problem, and in fact, we work with the U.S. Air Force and other air forces on this. But it's also a civilian problem. It's a commercial sector problem as well. If you pay attention to the news, and once you sort of learn about this problem, you start to notice it everywhere in certain areas of the world, say in the vicinity of Ukraine, or in certain areas in the near China. You'll often hear reports about GPS being blocked on commercial airlines or in boats, shipping container ships and things like that. And it's a real issue because the GPS system is very fragile. But luckily, there's a solution. There are many solutions to this problem, there's a whole constellation of potential solutions to this problem. And one of them, which is a key part of it, is the navigation via magnetic anomalies. So the idea here is simple. Along the Earth, you've got, magnetic field changes from place to place, but it changes by very small amounts. And if you had a magnetic map of the Earth and a device which was sensitive enough in order to detect how the magnetic field changed from place to place minutely, then you could figure out where you were and navigate without ever communicating with a satellite, say. And so it's an unblockable way of navigating, unjammable, unspoofable. And this is a thing you can do with quantum sensors combined with AI. And again, I've sort of already mentioned the problem. The problem is that if you've got, say, a quantum sensor on an airplane that's capable of detecting the tiny changes in magnetic field, well, it's also detecting magnetic field coming from all the electronics in the airplane and the engine and things like that. And if somebody, has a piece of metal on them and they move around in the cockpit, it'll detect that too. And so the real issue is an AI issue, a software issue, a denoising issue, a finding signal in the noise kind of issue. And that's a thing that you can do. And we've demonstrated that on real flights, navigating using this method in real time now, that this is this is a thing you can do today and will continue to build out into the future as an example of realizable solutions today involving this marriage of quantum technologies and AI. Another example that's along similar lines is in the medical diagnostic space. So everyone has probably heard of EKG, electrocardiography, right? This is a they attach electrodes to your chest, they measure electrical signals, and try to figure out, is your heart doing what it's supposed to be doing? And if you imagine if you go to the hospital reporting chest pain, this is the first thing they'll do, is they'll take an EKG to try and figure out, okay, is this person having a heart attack? What's going on here? And it turns out, and I didn't know this until we got involved in this area and learned a little bit more, that a huge fraction of the time, 30–40% of the time, if you go into a hospital with chest pain and they do an EKG, it will come back indeterminate. Like they won't be able to tell what's wrong using the EKG. But at the same time, it's known, thanks to older generations of quantum sensors, squid devices and things being used in a research setting, that the magnetic signal from the heart, much harder to detect than the electric signal, but generated because of, as a result of the same processes, right, actually can discriminate among things that the problems that the EKG can't see. So if you had MCG available in a way that was inexpensive and cheap, like an EKG, then this is a thing you could use to detect many heart attacks that today would require, a series of more expensive and more invasive kind of tests and injections and scans with more expensive equipment. So why don't people have these sort of squid devices, say, superconducting devices detecting MCG everywhere to improve? Well, that's too expensive. It'd be like having another device that's the size of an MRI machine. It has to, work, it has to live in a special room and so on. What we can do now with quantum technologies plus AI is take that idea and put it into a form factor that's more like an EKG or an ultrasound or something like that, like a bedside device that doesn't require you getting into a tube like an MRI in order to measure these magnetic signals. How does that work? Well, it's sort of the same 1-2 punch of quantum and AI. Quantum on the sensing side, like the actual sensors involved, they have to be compact enough and sensitive enough to detect, again, these tiny magnetic signals from the heart as it's beating. It's generating magnetic signals. And then on the software side, you want to say, all right, I'm detecting the heart as it's beating. I'm making a kind of map of the magnetic field that's coming out of the heart using an array of sensors. But I don't care about all of the other magnetic signals that are happening outside of where my patient is. I don't care about all the other electronics in the hospital. I don't care about people moving metals around. I don't care about the elevator going up and down, 300 feet away. I only care about what's happening with my patient with the heart. And so the thing that AI lets you do that the quantum sensors wouldn't let you do on its own is do this in a way that's unshielded MCG. So you don't have to be inside of a tube that blocks out all the magnetic fields. You do that at a software layer. And this is another thing that we've been able to do. We're working with a number of clinics, hospitals, such as like the Mayo Clinic, for example, where this is being tested right now with real patients, and it's actually working, right? So this is an example of a quantum plus AI solution which exists today, right? It's not the kind of thing that we have to wait more for the technology to develop. Of course, the technology will get more impressive over time as it develops, but again, what we like to focus on is things that you can do today as stepping stones and toward the future technologies and keep the market interested as the technology develops. As a final example, I'll come back to the computing side. This is similar in spirit to a lot of things that were mentioned in earlier parts of this session. When looking at drugs and materials, this is a natural place where you say, oh yes, this is a quantum problem. I want to calculate. I don't want to have to mix chemicals in my lab to figure out everything that I need to know about a material or a drug. I want to be able to do all of that on a computer. I want to speed up my iteration cycles, right? My throughput on how much I'm able to test and figure out and validate. And yes, one day when you have a quantum computer, the hard quantum piece of this you can pass to a quantum computer when it's able. But a quantum computer will never act on its own, work in its own way on this kind of problem. Really, it's sitting inside of a much larger, mostly classical computing workflow that looks at all the space of possibilities and, with a funnel type process, goes from anything that you could possibly imagine building or possibly imagine creating in your lab down to something that solves the problem that you're interested in. And the real challenge is connecting the dots between what's happening at the molecular scale and what happens at, say, the macroscopic scale. So if I design a drug, right, and I eat it or I ingest it, will it kill me, right? Is it toxic? That's a very complex biology kind of issue. That's not a thing that you're going to be able to calculate from first principles, even with a quantum computer, right? And connecting what you might see at the macroscopic scale down to the molecular scale where you can do your quantum calculations, that's where the AI comes in. That's the AI plus the quantum. And those pieces, those connective pieces where you work on how to do the optimizations given calculations at the molecular scale, those are things that you can do today. You can start to refine those today, focusing on those parts of those areas where you can get away without the quantum computer at the molecular scale. A lot of molecular scale stuff can be done with GPUs. You don't need a quantum computer for everything at the atomic scale. And certainly you wouldn't use a quantum computer for the rest of it. So putting together these kinds of workflows is another important activity as we prepare for the eventual quantum future. And this is another thing that we've done at Sandbox, and we do at Sandbox, and we work with a number of partners in the biopharma industry and materials, batteries, things like that, to do this kind of thing. So I think that's, yeah, so those are the examples that I wanted to view and really paint this picture of AI plus quantum ecosystem coming together to solve problems today, not just 5 years from now. Thank you.
Thank you very much.